残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には遥か未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
I mean, yeah, I know it's Craigslist, but it's a nice wooden bowl. No, $1.50 is not a reasonable price. No, you can have the ashtray that looks like a cat. Yeah, you can have that for $1.50. No, I don't care. Oh, hello. Let's get started. Okay, what's up guys? We're back. We're talking a little bit more about approximating the area under curves. We're talking some more about Riemann sums. We're going to get a whole lot better way to deal with all these things. Definitely a lot better way to write a lot of related concepts involved. So, as you probably noticed last time, working with Riemann sums is insanely annoying and very cumbersome with even a relatively large number of subintervals, let alone a large number of subintervals. So we're going to pause for a moment and introduce a little bit of notation to simplify our work. And we're just going to simplify our lives substantially. This will make everything way, way easier. It's called sigma, or maybe if you want to, summation notation. And it's used to express sums in a really compact and nice way. So for example, the sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, it's not even quick to say. It's definitely not quick to write, involves 10 terms. Most of the time we just throw these little dots in there if we're trying to represent it. But this isn't very precise. It's not really very mathematical, right? You know, it's kind of a little bit of guesswork inferring what it's supposed to be. It's sort of easy for something like this, but for more complicated sums, for more complicated things you're adding together, oh my god, it could be a nightmare. So, what we're going to do is we're going to use this new notation to write a sum like 1 plus 2 plus 3 all the way up to 10 in a much easier way. We'll write it like this. So here's how you'd read it. The sum from k equals 1 to 10 of k is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Here's how the notation works. This big, weird E-looking thing is a capital Greek sigma, which is like the Greek capital S. It stands for sum, S for sum. The index, as we'll call it, k, it takes on all integer values from the lower limit, here that's k equals 1 in that example, to the upper limit. So lower limit to upper limit, the upper limit is 10. So we don't write the k equals up top just because we already wrote it down low, but the basic gist, this part says sum, this part down here, k equals, n from n to, and let's just put like an r up here, sum from n to r, and then you have some stuff afterwards. And that's what you say of. So sum from k equals n to r of some stuff. Here we have the sum from k equals 1 to 10 of k. Okay, it just follows this exact form. It's even pretty easy to read out loud. Nice. So that expression that immediately follows the sigma is called the summand, and it's evaluated for each value of k, and the resulting values are all summed together. The basic gist of it is that your k is a counter. This guy is a counter. So you start with the low number, you put it down, then you increase it by 1, and you put it down. Then you increase it by 1, and you put it down, and you go all the way until you hit that top number. This is when you stop. So it's basically like a little program. It says, hey, start here, increase by 1 every time, and put a plus in between whatever you get. So you can sum up a lot more complicated things this way. Here's some good examples. So if I wanted to sum up k from 1 to 99, the sum from k equals 1 to 99 of k, that would be 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way up to 99. That's a 99 term sum. I wouldn't want to write it down. I definitely wouldn't want to read it. It's almost impossible, just for the casual reader without a lot of work, to tell whether or not you're adding all the numbers except maybe like 39 or all the numbers from 1 to 99. This is an easy way to compactly say that, yeah, we're adding all of them from 1 to 99. Otherwise, you'd have to go through every term and see which one was missing, or if any were missing. It'd be a mess. This is way more convenient. So we could try another thing. We could mix it up, make it way more interesting. Instead of just adding consecutive numbers, we could do cooler stuff. For example, we could take the sum from k equals 1 to 3 of k squared. That is, starting at 1, we get 1 squared plus 2 squared plus 3 squared, and now we've hit our upper limit, and we can stop. So that ends up being 1 squared is 1, 2 squared is 4, 3 squared is 9, so that's 1 plus 4 plus 9, that's like 14. There you go, cool. We could even mix it up and use whole expressions. Stuff like the sum from k equals 1 to 3 of the quantity 2k squared minus 1. This would be the quantity 2 times 1 squared minus 1 plus 2 times 2 squared minus 1 plus 2 times 3 squared minus 1. Oh wow, that's a lot more interesting. You can do very complex sums that I don't think would be easy to recognize what you're doing without this notation. So this is really nice. Now you might have noticed that there's a variable here, the index, the k. This index is maybe your first example of a dummy variable. So it's internal to the sum. It doesn't matter what symbol you choose as an index, because by the time you evaluate the sum, it's already gone. So, for example, the sum from k equals 1 to 99 of k is the same as the sum from n equals 1 to 999 of n, and that's the same as the sum from t equals 1 to 999 of t. So, all the same, because the dummy variable doesn't matter, by the time you actually add these up, there's none of them left. Notice, up here, there's no k left over when we're done. There's just a number. The k is gone. So it doesn't matter. It's not like we're introducing a new variable. It's just basically a symbol to represent the counter we're using. Okay, so it's pretty convenient, and you can do a lot of nice stuff with summation notation or sigma notation, whatever you want to call it. So one nice thing is that you can factor a constant multiple out of a sum. So we can factor a constant multiple out of a sum written in sigma notation. Same dang thing, just written in a different way. So statements like, the sum from k equals 1 to 43 of 9 times the quantity k plus 2 is equal to 9 times the sum from k equals 1 to 43 of the quantity k plus 2. These are totally fine and mathematically valid. Totally reasonable. You're just pulling a 9 out from every term. Easy. Okay. So we can also break up sums along indices. And this is when it starts to look a little more confusing, but it's not actually bad. So if I took the sum from k equals 1 to 43 of the quantity, or of 9 times the quantity k plus 2, I could definitely break that up into the part of the sum that goes from k equals 1 to 16, and then the part of the sum that goes from 17 up to 43. I can do part of it, then do the rest of it a little bit later. That's totally fine. That makes some good sense. We're all set there. I don't think that's confusing. You can also break it up along terms of the sum, and this is where you sometimes have to be a little bit careful, because you need to respect the usual algebraic operations. So for example, you could take the sum from k equals 1 to 11 of k plus k squared, and you could break that down into the sum from k equals 1 to 11 of k, plus the sum from k equals 1 to 11 of k squared. This is kind of nice. This is a reasonable and convenient thing to do. If I'm adding up all these things together, I could just rearrange the order of addition and result in this. Pretty convenient. Okay. So all of the nice properties of sums carry over into sigma or summation notation. They just might look a little bit more confusing if you're not used to working with it. But once you get used to working with it, oh, you never go back. It's amazing. It's so much easier. So here's some nice stuff. Now we can actually write some of these statements in a very convenient way. So for example, here are some great facts about sums of powers of integers. So for example, let's let c be a constant and n be a positive integer. Then we have the following. The sum from k equals 1 to n of a constant, well, there's no index in there. Nothing's changing. You're just adding together c n times. So this guy is just c plus c plus c plus ... plus c, and there are a total of n of these. So that's c times n. 2 plus 2 is the same as 2 times 2. 2 plus 2 plus 2 is 3 times 2. So there we go. That's pretty fair. Some of the rest of these are a little bit more interesting. So there's some famous stories about people figuring out this formula. I'm not sure of the veracity of them. I suppose I could check. But supposedly, at some point, a famous mathematician was asked in grade school, in primary school, to sum up all the numbers from 1 to 100. And the teacher thought it would take them a long time. They were just sick of the kids, needed a little bit of a break from all the hustle and bustle. And suddenly this mathematician rolled up and was like, I'm done. Little kid. They were like, no way. How did you do it? And they figured out this trick to add up this nice sum, the sum from k equals 1 to n of k. Whoa. And as it turns out, if you add up the numbers from 1 to some number n, you get n times n plus 1 over 2. Whoa, that's a pretty good trick. That's a pretty convenient little fact. So, for example, the sum of the first 100 numbers from k equals 1 to 100, that's 100 times 101 all over 2. Oops, wrote that a little bit wrong. Wrote it a little bit too fast. Okay, sum from k equals 1 to 100 of k is 100 times 101 over 2. So that's just 50 times 101. Or maybe a little bit easier said, that's 5,050. Nice. Okay, so now you can do an amazing party trick if you don't like getting invited to parties. Okay, cool. There are similar formulas for the sum from k equals 1 to n of the first, of k squared, of the sum of the first n positive integers squared. As it turns out, it bears a striking similarity to the sum of the first n integers just by themselves. So the sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 all over 6. And the sum from k equals 1 to n of k cubed is n squared times n plus 1 squared all over 4. Pretty convenient, pretty nice. It's cool that we have these formulas. We won't spend our time looking at how you get these. It's pretty nice. There are some very fun, cool little tricks. Maybe if we get time, we'll do it in a bonus math video. But for right now, we'll just use these. They're very convenient and they're pretty neat. So let's see how much easier this makes calculating a Riemann sum. Okay guys, so for one, using sigma notation or summation notation makes the definition of a Riemann sum way easier. So to start with, let's just look at an alternate definition of the Riemann sum. It really is exactly the same, just written with different symbols. So same assumptions. We're going to suppose that the function f is defined on a closed interval from a to b, and that we're dividing this guy into n subintervals of equal length, which we'll denote by delta x, like we talked about before. So if xk star is any point in the kth subinterval, like we drew all those pictures last time, which the kth subinterval, by the way, in case you forgot, is the interval from xk minus 1 up to xk, and we're only talking about this when it makes sense for the n subintervals that we have. All right, so the Riemann sum, or a Riemann sum of f on the closed interval from a to b, is just, and this is the form of every Riemann sum for some xk stars, the sum from k equals 1 to n of f of xk star delta x. That looks way more compact. Before, we were writing it out in the full expanded form, which was this nightmarish thing. This thing was equal to, f of x0 star delta x plus f of x1 star delta x plus dot 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 f of x xn star delta x. I barely even have room to write it. It's a mess. It's crazy. No one wants to work with that. Let's just not even bother. This is what we'll be calculating. But look how much nicer it is over here. That's way, way, way nicer. Cool. So the three common cases we talked about that occur in practice, the left, right, and midpoint Riemann sums, take on a far easier form here. However, they look a little bit more confusing at first. Don't let this throw you off. They're not any more difficult to do. They're still annoying to do, but they just look a little bit different when they're written compactly. Luckily, though, this makes it much easier to deal with them. So, the left Riemann sum is the sum from k equals 1 to n of f of the quantity a, the left-hand endpoint, plus k minus 1 delta x times delta x. So here, xk star is xk minus 1. And as it turns out, there's a very nice way to write out what xk minus 1 is. You just go k minus 1 delta x's from where you started. So when k is 1, you just start at the left endpoint. When k is 2, you go 1 delta x further. This follows exactly what I was trying to say last time with our little procedure. So you start at A and you're going to B and you've got n subintervals. Let's say here we've got, I don't know, let's just do 3. So you start at A, that's x0, and then you go 1 interval over and you get x1. You go 1 interval over again, you get x2. You go 1 interval over again, you get x3. But when we're doing a left Riemann sum, we only pick up 3 of these guys because we only have 3 intervals. You only pick up 3 of them for a right Riemann sum too. It's just which 3. So for a right Riemann sum, I would pick up these guys right here. So I start with no delta x's over, and then I go 1 delta x over, and then I go 2 delta x's over, and then for something like this, I'm pretty much done, right? I start with 0, and then 1, and then 2, and if I've got 3 subintervals, I'm done. So that's how a left Riemann sum works. For a right Riemann sum, the only difference is I have a k instead of a k minus 1. That is, I start one of them over. So for the right Riemann sum, I start at x1, I go over a delta x, pick up x2, and then I go over one more delta x, and I pick up that x3. Nice. Now, of course, on the right Riemann sum, I would still label these all x0, x1, and x2, but just keeping consistent using the same labeling scheme, it would be x1, x2, and x3. But, for each of these, we'll use their own internal labeling scheme just to keep things consistent. But there we go. All right. That gives us the right Riemann sum. The midpoint Riemann sum, we're just going, it's slightly more confusing. Instead, we go k minus 1/2 delta x's further. So that would be we go half a delta x, and then we go another delta x past that. So in this little picture, if I can kind of duplicate, here's halfway after like half a delta x, right? And then I'm going to increase by 1, and I go 1 delta x further, a full interval length, and then a full interval length. So I'd be picking up this guy, and this guy. That would be my x0, x1, and x2. Okay, very cool, very convenient. These are my xk stars here. Nice. All right, convenient, nice, very cool. Let's actually do an example. Okay guys, we're pulling out the big guns here. Gonna do example 2. We're gonna evaluate the left Riemann sum for the function f of x is x to the third plus 1 between a equals 0 and b equals 2 using, drum roll, 50 subintervals. That's a lot. If we try to do this by hand, if we try to do this without using the nice summation notation and those identities we just learned, it's going to take all day. It's going to be a mess. There's no reason you should do that. This will showcase why we would even bother with something like summation notation, why we would even bother with those identities, why any of this stuff is useful in the context of approximating areas under curves. So let's start it off. With n equal to 50, the number of subintervals being 50, the length of each subinterval, which remember we're denoting by delta x, is just the length of the interval. That's 2 minus 0 since we're going from 0 to 2. So 2 divided by 50. We're just splitting up the interval into 50 pieces. So you take the total length divided by the number of pieces you want. So 2 divided by 50 and you get out delta x is 0.04. Okay, cool. We've got the width of each of our boxes. Now we need the height of each box. So the value for xk star for the left Riemann sum, like we just saw, is given by the formula xk star equals a plus k minus 1 delta x. Now plugging in our delta x and plugging in our a, we're going to get 0 plus 0.04 times k minus 1. I wrote that delta x on the other side just for convenience. Okay, cool. We don't need to write that 0 plus since it's just 0. And let's bring this 0.04 on through. We'll get that xk star is 0.04k minus 0.04. Cool. We've got the length of each interval, and now we've got our xk stars. To get the height of each of our boxes, we're going to need to plug this into our function. That is, we'll find f of xk star, which, using our formula for xk star, is just f of a plus k minus 1 delta x. We already computed that right up here, so we might as well just plug it on in to f. All right, f of x is x to the third plus 1. So I'll just replace that x right there with what we've got here, 0.04k minus 0.04. So I get 0.04k minus 0.04 all to the third plus 1, since I've got that plus 1 at the end there. Cool. All right, so I've got 0.04k minus 0.04 to the third. Let's not spend a bunch of time expanding that out. We all could do it if we wanted to. It just might take a little while. Let's save ourselves some time. What you'll end up getting is that f of xk star is equal to 0.04 to the third, k to the third minus 3 times 0.04 to the third, k squared, plus 3 times 0.04 to the third, k, minus 0.04 to the third plus 1. Cool. All right. Bit of a mess, but we did it. It's not terrible. It's just a polynomial in k. I haven't written out those 0.04 to the thirds in terms of a long decimal. I'll just leave them like this. It's all good. We're going to punch something in a calculator at the end of the day anyway. So let's just leave them like this for convenience. All right. Now we're just going to use the formula for a left Riemann sum. So let's scroll down a little bit here. Cool. We got our f of xk star. And we've got our delta x. We're ready to go. The left Riemann sum is given by the sum from, in this case, k equals 1 to 50. Because we're doing n equals 50, this 50 right here, that guy's just n, of f of xk star, which in our case will be a plus k minus 1 delta x, all times delta x. Just plugging in what we got here in this first part, this big guy right there, this is just f of xk star. Cool. And then right at the end, I've got my delta x. All right, so I just replaced the f of xk stars with what they actually turn out to be. I plugged in my delta x, and we're good to go. We can go to the next line. So notice, every single term in this sum here has a 0.04 in it. Since I can always pull a constant multiple out of a sum, I'm just going to do that. That is, I'll take this 0.04 and I'll pull it all the way out front. That's how I get this 0.04 right there. This guy, that's still just our f of xk star. Nothing has changed. That's still just f of xk star. All right, cool. So now I'm going to do a couple steps at once. Basically, I'm just going to use the fact that I can split up a sum across its terms. So this big long sum, I can split it up into this guy, this guy, this guy, and I'll put these two together just for convenience because they're both constant terms. That is, I'm going to split this up into powers of k, and then I'm going to pull out all the multipliers. So I split the sum up into each piece, then I pull out the coefficient. That 0.04 just hanging out at the beginning. We're not doing anything with it yet, but I'm just splitting up the sum here. So 0.04 times this huge quantity where I've split every term up. That is, I've got 0.04 to the third from this guy here, times the sum from k equals 1 to 50 of k cubed. There we go. Minus 3 times 0.04, that's this guy here, time 0.4 to the third, times the sum from k equals 1 to 50 of k squared. That's that guy right there. All right, plus 3 times 0.04 to the third. This guy here is just that guy right there. All right, all good, all good. Times the sum from k equals 1 to 50 of k. That's just this guy right here. All right, and then for this last term, the constant term, the stuff without k's next to it, I'm just going to write it in a slightly different order so we don't make any mistakes with our signs. That is, instead of writing negative 0.04 to the third plus 1, I'm going to write 1 minus 0.04 to the third, and the sum carries over there as well. So this piece right here gives us the term in this expansion, the sum from k equals 1 to 50 of the quantity 1 minus 0.04 to the third. Cool. It looks messy right now, but we can deal with each one of these guys separately using the identities we already know. So I'll put those up here real quick. Bam. All right. Let's plug and chug. So this sum from k equals 1 to 50 of k to the third becomes 50 squared times 50 plus 1 squared all over 4. So I just replace it with that right down here. The sum from k equals 1 to 50 of k squared becomes 50 times 50 plus 1 times 2 times 50 plus 1. So that's 101. And all of that's over 6. So I get this term right here. Then this sum from k equals 1 to 50 of k becomes 50 times 50 plus 1 over 2. I replace that with this guy right here. And then this last one, this is just the sum from k equals 1 to 50 of a constant term. So I get 50 times that constant term, and I replace that guy with this right here. All right, cool. So it's a lot of numbers, but this is what we got calculators and computers for. Plug and chug, throw it on in a computer, throw it in a calculator. Bam, you get out 5.8416. Exactly, no rounding actually. All right, cool. We did it. It looks messy. It looks tricky. It's not. It just takes some time, and you have to be a little bit careful. Make sure you're not making any simple sign errors or arithmetic mistakes. All we're doing is we're using some identities to take a complicated looking sum and expand it. These identities make it really convenient to calculate Riemann sums for stuff involving polynomials. If you're using a polynomial, you're just going to end up getting powers of k somehow for the left or right or midpoint Riemann sum, and we can handle those guys. So this is why we'd even care about, these identities involving sums of powers of k. It's useful when we're computing Riemann sums. All right, easy enough, kind of cool, but there you go. You've got it down now, or at least you've seen it in action, and while it's not very fun to do these, no one likes doing them, it is interesting that we're capable of doing it. Now, granted, that being said, outside of a couple problems like this you might do in a class, generally, don't spend your time doing this. This is what we have computers for. This is long, this is tedious, it's not enlightening. Use the technology you have to make your lives easier. All the same, it is interesting that we are theoretically able to do this. Cool. Ugh. Yeah, I'm a detective. So what? I can spot a lie from a mile away. Think that makes me the best? No way, buddy. Any closer than exactly 1 mile, and I'm fricked. I can't tell if you are lying if we are under 1 mile, pal. Under 200 feet. Can't even understand English. I haven't talked to my son in 24 years. My ex-wife, Carol, she left me. This is ruining my life.